It is my pleasure to introduce Professor Vijay Chidambaram, who's an associate professor at the Computer Science Department at the University of Texas in Austin. So he got his PhD from University of Wisconsin at Madison, and then he did a postdoc at VMware Research Group. He's known for his research in file systems, storage systems. He has won many Best Paper Awards, including at ATC and the FOSS conferences. He also got the NSF Career Award in 2018 and SIGOP's Dennis Ripley Dissertation Award in 2016, Microsoft Research Fellowship before that. So, and many of his techniques has been commercialized or has gone into part of Linux kernel. So today he's going to talk about how to build a storage system for new application and the new hardware. So what do you?
Thank you, Arthur. Can everybody hear me? Microsoft. All right. My name is Vijay Chidambaram. I did my PhD in Wisconsin with Arka, so we were there at the same time. So it's my great pleasure to come here, like so many years later, and present to this. All right. So let's get started, right? So any major thing that you do today, right? Whether it's like cloud services or mobile applications, games on your phone, anything, right? One of the central foundational things that everything depends upon is storage services. It's a very unglamorous part of systems work, but it is sort of very foundational and everything sort of like depends on it, right? And for a very long time, storage was very boring because like we used to have like a disk and nothing else, and like we were like, can we optimize the spindles and like for a long time, very boring stuff. But this is changing now, right? So if you are in storage today, like we actually, it's a very, very exciting time. So part of the reason is that new hardware is coming out. So persistent memory has come and gone from Intel. Other people are also working on persistent memory. DNA storage is on the horizon. Intel and several universities are working on this. Project Silica is where you write your data into glass. And so like you can have like hundreds of terabytes on like a glass this size. And this has like apart from sort of like density, it has some other nice properties also. For example, both DNA and Silica are very resilient. Like if you write data on these things, apparently they can last for like thousands of years, which you wouldn't get if you store it on a magnetic drive or an SSD. So they have interesting properties. We also have new applications which are putting stresses on the storage system in new ways. Like the theoretical examples are like machine learning and like blockchain. But we also have new data privacy regulations like GDPR from Europe, which also has interesting takes on like how can you store data, how can you process data that wasn't there before. And we also care about new things now. Like so back in the day of the disk did not degrade significantly over time. But if you consider solid state drives and other things we're producing today, like persistent memory, they all have limited lifetimes. So you buy an SSD and you put it into your computer, and you can only write to it a certain number of times, after which it gets bricked. You can no longer use it. So if you are not careful in how you write to your storage devices, they will get bricked and you have to replace them. And at the scale of like Google and Facebook and so on, this is a significant cost. Typically, what they will do is they will replace their storage devices every 3 to 5 years. They'll get a big, massive wholesale deal in which we do this. So if they're forced to replace their drives like every year or every 2 years, it's very inconvenient and expensive for them. So now we care about this stuff as well. So this is what my group works on. So at University of Texas at Austin, like we have been working on challenges related to storage over these years. So back when I did my PhD at Wisconsin, my bread and butter was storage reliability. Like I worked on how do you make file systems more reliable. So since I came to UT, I've been continuing that line of work. So we have done work on that line. We have worked on distributed storage systems. Like if you're familiar with Raft, we have looked at if you have storage faults in Raft, what would happen. And we have some very counterintuitive results. Like in a distributed storage system, typically your data is triple replicated. So it assumes that if you have a storage fault in one of your copies, the other 2 copies can be used to fix it. What we instead found was there's a problem in one of the copies, it then spreads to your other 2 copies. So if you're not careful about your protocol, simply having multiple replicas is not enough. So that's something that we found. We also worked on write optimized storage. So that relates to what I just talked about with the limited lifetimes. So A write optimized storage is something where it takes care to write the minimal amount of bytes down to the storage device so that it lasts for longer without giving up performance. So we have done some work there. And this is what that has been adopted by VMware. So right now, in fact, I am actually on a sabbatical with VMware in sort of helping them. We have worked on storage for persistent memory, which is like like an interesting tale whereby Intel for a very long time used to say next year we'll have persistent memory, next year we'll have persistent memory. This went on for like a decade. And then in 2018, they actually released persistent memory, and people are very excited. We started working on this. And quite recently, they have said we will no longer produce this. And so it's a very interesting tale. Thankfully, there are other people working on persistent memory, so the research still has some value. We have also worked on systems for machine learning. Like how do you build data pipelines? Do they matter? How does it work? And also storage for new regulations such as GDPR. So I have like a bunch of meetings later in the day, and I'm hoping to meet like most of you. And like we can talk about any of this stuff, like a very neat one-on-one. In the talk, I'm going to focus on some of these words to give you a flavor of the kind of research that we do. Okay? All right, so let me start with like talking about new storage technologies. And persistent memory is what I usually talk about. So this was announced in April 2018, and this is a unique kind of like storage device. So it's connected directly to the memory bus, similar to DRAM. So just as you would access your DRAM using like load and store instructions from the CPU, that's how you access persistent memory as well. It has slightly higher latency than DRAM. So if DRAM is like 50 nanoseconds, you could imagine this would take like between 100 to 200 nanoseconds. The read bandwidth is a little bit lower. The write bandwidth is significantly lower. So one way to think about persistent memory is that it's a persistent device that is connected to your memory bus that acts as sort of like a poor man's DRAM. It's slower, it doesn't have as much bandwidth, but it is persistent. So if you lose power, all the data that is in persistent memory will remain, unlike DRAM. Okay? Now, even though the way I'm saying it here, right, it seems like pretty bad compared to DRAM, it is about 1,000 times faster than the next thing, which is solid state. So from the viewpoint of like storage devices, this was a significant step forward. So quite recently, Intel announced that they're stopping persistent memory products, which is like highly unfortunate. They were losing a lot of money on this. So in some sense, like the writing was on the wall, but also we felt that they would, continue working on it and eventually make it profitable, but like it's not to be. But there are other people working on this. For example, Samsung is working on something called Samsung Memory Semantic SSDs, which they announced earlier this year. So this interface where you access storage through like load and store instructions similar to DRAM, it's like we call it byte addressability, and where it's like if performance is close to that of DRAM, is something that a lot of people like. For example, if you have like giant graph data sets where you're doing random operations, having something like this actually helps quite a bit. So anyway, so that's what persistent memory is, and we had a lot of work over the years about like how do you build data structures for persistent memory, file systems for persistent memory. In fact, like I'm not even showing some work in here, which like it was in the 90s, like or even like in the 60s, where like they were like, if persistent memory looked like this is how we would build a file system. So there's a lot of work there. But the work that I'm showing you all we did once we actually got our hands on the real device. So it's tailored to that. So let's start by considering using persistent memory as a storage device. So we're going to have a file system on top of it, and we're going to look at the time taken to do a very simple operation, appending 4 kilobytes to a file. Very common operation in multiple workloads. Okay. So if you look at it here, right? So this is the y-axis is in nanoseconds, x-axis is the device, and several file systems. So if you look at the device, if you write 4 kilobytes to the device itself, that takes only 700 nanoseconds. Quite fast, right? Even with sort of like low latency SSDs, it is very challenging to do this in less than 1 microsecond. So this is like big leap forward. But if you look at sort of ext4, which is the mainline Linux kernel file system, if you did this append operation through that file system, it will take you 9,000 nanoseconds, order of magnitude more, right? And we call this software overhead. The difference between what the device itself can give you and what your file system is. And clearly, this wastes all the potential of the device, right? Like we now have something that can do sub microsecond offense, but now we are doing 9 microsecond offense. So it's like, quite a waste of the device. So research file systems have worked on getting this lower, right? So 12x is industry, right? And that's what we are currently getting. But there have been research file systems from Georgia Tech, San Diego, UBS, which have reduced it to about 2.5x. So then the question is, can we do even better? Right? So even 2.5x in our view, when we started this project, was like, quite high software overhead. So the big research question that we tackled in this project was, how do we decrease the software overhead of persistent memory file systems? And the central idea is this. So we're going to handle data operations in user space. Because what we saw was that when we looked at what ext4 was doing, a lot of the time was spent just trapping into the kernel, right? So every time you want to do, like, how do you do normally, right? Like IO, like you do a system call for everything. A system call is very expensive. You have to trap into the kernel, you have to change context, you have to flush caches sometimes. So it's a quite expensive operation. So we don't want to do that. We're like, they're going to do the data operations from user space, no trapping into the kernel whatsoever. Okay. The other interesting part of this project is that we want to handle the metadata operations, things like creating a file, renaming a file, deleting a file, all of these things. We want to do them via the kernel. So we want to trap into the kernel to do this. But not only that, we are going to say, as in like, this project is not going to handle them at all. They're going to allow ext4 to handle them for us inside the kernel. Right? So this is basically saying we will do data, all the metadata, we're going to push into ext4. It's already there in the kernel. We're going to use that to do it. Okay. So why are we doing this? Right? So this project was a collaboration with Sanidhya and Kesu at Georgia Tech. Sanidhya is now a professor at EPFL, and Ashish Kohli used to be at Penn State, now he's at Google. So I've given you the general idea. Why are we doing it? So the main idea is that data operations are simple. From a file system point of view, data operations are relatively simple. So if you want to read a file, you want to write a file, not append to a file. Append is a metadata operation. But if you just want to write to a file in place, it's a relatively simple operation. You have to find out where is the block of data that you want to write. Just you go and do a device operation. We can do it at very low overhead from the user space. On the other hand, metadata operations are very complex, right? So if you look at the POSIX standard, you do file create, rename, all these things, they have so many flags. In fact, like I have a paper from grad school where we showed that most people mess up on these things. Most file systems have bugs in implementing metadata operations. Very, very complex and hard. So we don't want to redo all of that in our project, right? So if I'm building a new persistent memory file system, I want to re-implement all the metadata operations. Right? I mean, it's a lot of overhead. So then the question is, what can we do, right? And so our idea was, we will allow ext4, which has been in the Linux kernel for decades, with like lots and lots of work that's gone into it. We will allow it to do metadata operations. And when you're making the design choice, we are consciously saying metadata operations will be slow because you have to trap into the kernel. ext4 is not particularly designed for persistent memory. It's not going to be doing it today. But our sort of bet is that if we can accelerate your data operations enough, it's okay if you take a hit on the metadata operations. So that's the overall idea of the project. Feel free to interrupt me at any point of time and ask questions. Like I can tailor the talk to it. Yes.
So I think in operating system there are cases where you can data has been written, it can remain in the main memory and it can be sent to the exactly.
Yes.
So why do we want to reduce from 9,000?
So I think if I understand it correctly, the question is, if you can cache all your data, what does it matter what the latency of the operation is? Would we not get DRAM latency anyway? Is that correct? If not, please clarify.
Operating system has
yes.
To write, it can be written into the
yes,
RAM,
yes.
It can be
correct.
later.
Mm-hmm.
And if you want to read the same data again, you can read it again from the RAM.
Yes.
So why do you need to flush instantly to the flash?
Great question. So the main thing is that your semantics of when you flush your data and when you read your data, not all applications are meant to be the case where you can flush later. So the main risk that you get when you say I'm going to flush later is that If you lose power, the data is gone. So you can imagine that a bank, for example, when you put in money, it does not want to keep the data in DRAM, right? It wants to make it durable and durable on multiple places. So there are certainly applications where you can buffer it in DRAM and like you basically get like DRAM speeds. But there are definitely applications where you need immediate persistence and durability at the end of the system call. So that's one part of it. The other part of it is that even if everything was on DRAM, right, the cost of the system call is still there. So if like in the graph that I was showing you, right, if everything was like replaced instead of persistent memory, we had DRAM, the software overhead that you're seeing is not due to the device, right? So if you replace with DRAM, the software overhead will become in fact higher because the device has become a little bit faster and your overhead still remains. So all of the things that we're CPU instructions, the locks that we're getting, all of these things that we're doing, right? It doesn't depend on the underlying media. So that's what I'm trying to say, right? When we say that we want to do data operations from user space, we are in fact cutting out all the cruft, all the things that you do when you do an operation via the phone. Yes. Yes. It includes the metadata cost.
So what fraction using that R be the contribution?
So here, right? Yeah. So this is just writing 1 4 kilobyte, and this is like the full operation. Like if your file system writes a lot of extra metadata, it will have a lot of cost. If it has low metadata, it will have low cost. But if you look at it, a lot of the cost is in fact metadata, right? And that is actually like a hint to how we do better also. Like we reduce the amount of metadata that we do.
So I know it was getting out of the like they have a sense of the cost per storage of persistent memory and also its durability compared to
So let's see, right? So the durability part is easier to answer, so I'll answer that first. So when Intel was doing DC persistent memory, you could do about 1 million writes to a cell before it would so that was the durability. And if you calculate that in terms of how much data could you pump into it, it was like some absurd number, it wasn't like petabytes, like for a single 512 GB thing, you could write petabytes of data before it would come. So we briefly investigated this to see if there was write optimizations that we have to do to sort of make it, but we felt that that was not the first problem to tackle because Intel has enough redundancy in there that for at least for some time this would not be a problem. So that's it. In terms of cost, it is actually a little bit cheaper than DRAM. So the cost, if you look at it, DRAM is still per GB the most expensive thing. Persistent memory is a little bit lower than that, and then SSD of course is even cheaper. So the costs tend to go down like that.
Makes sense for Google or Facebook in terms of PC.
Yes. All right. Okay. So let me keep going. So we talked about this. Okay. So let me actually split this into a little short. This is just how it fits into other related. So this is what the file system. So we have an application, a process in user space. So we have a library that will attach to that application, which we innovatively call uSplit. And then we have a kernel split, which is just ext4 in direct access mode. So when the application is doing the read or write, one important thing I want to mention is that the application in all of this is not modified at all. It's an unmodified application. So basically tracking all the read and write calls, your library will then change that into the appropriate operations on persistent memory. In this part, there is no kernel interaction, right? No traps, nothing. So it's only quite fast. So if it takes 700 nanoseconds to write something, it's going to be a little bit more expensive, but close to that. Whenever you're doing metadata operations like create or delete, it will once again be got by a user library to then send it to KSBit, to ext4, to then do it on the file. One other thing that we did was that we also have a log per uSplit library. And this log allows us to view properties like atomicity. So if you want your system call to be atomic, you need a log in order to do that. And so that log we can read and write directly from user space. It's not inside the kernel. So common case operations like read and write, this is the bulk of most workloads we can accelerate, and we reuse ext4 DAX for the metadata operations. Yes. Yes. Great question. So typically, when you're doing read or write, you will have a handle to that particular file. And when you're opening the file, that is a metadata operation that still goes through the kernel. So you already have done all the security checks before getting to the read operation. Right. So okay. So this is our performance effect. So the same graph, same x-axis different file systems and device, y-axis is now. So SplitFS has the file system is called SplitFS because you have split architecture. It has a number of modes, and split is a mode where all our system calls are going to be atomic and synchronous. Anything that you write, system call completes is already durable. We can lose power, we are fine. It's also atomic. So if you're writing, let's say, 256 megabytes and you crash, either all the 256 megabytes will be there or none of the 256 megabytes will be there. So these are not properties provided by, for example, ext4 lax. So not only are we providing stronger properties, but we're able to do it at like lower cost. Right? So about like the cost that SplitFS has is about 80% of like one extra 4 KB block. So if you write the 4 KB block, so this is common for everything, we have about 80% extra on top of that. Right? So so in the paper, if you look at it, we have run like bigger workloads. I just showed you like one example. But we have run things like like database applications, like key value stores, and we see that our initial assumption holds. In most of these applications, there are enough data operations that overall performance is increased, even though on a metadata operation basis, we are in fact slower. Okay? Bad use cases for SplitFS would be something like Git, where you're creating lots of small files, right? So there's not enough data operations to amortize our cost, but if you're creating a lot of files, that's all metadata operations that has overhead. So Git would be a bad example for us. Now we have spent a lot of time in making sure that SplitFS can be used by external folks without our help. So if you are working on persistent memory, I think get to that, or you are working on something else and you would require like a nice file system to work with, please contact us and we'd be happy to help you. So that's now I'm going to transition into the second part of my talk. Yes. Yes. Yes, that's a good point. So just to repeat the question is the idea specific to persistent memory? I don't think it's specific to persistent memory. I think any sort of like very fast hardware that you have, where your data access latency and the metadata cost is going to be significantly different, you can use a split architecture to derive similar benefits.
What I'm getting at, like, even if you have to
DRAM? Yeah. If you're building a DRAM file system, yeah, it would help. Now, I think like some of the aspects would no longer make sense. Like for example, we have durability, which you won't get on DRAM, but yeah. Yes.
When you do a write, is there a copy particularly going to the point of
Are you talking about like a DRAM to persistent memory copy or?
Which is where does the benefit come from? It just seems like display and then nice to have.
Yes. Yes.
What is the key aspect that caused that?
Yes.
Memory copy reduction and something else.
It's basically like
a memory copy also.
It's not primarily memory. So if I were to say what is the significant thing that is caused in the memory? One is that in this part you have kernel cache. Do all of that. Also, the code part here is significantly more complex than the code part. So when you consider something like, for example, appending to a file, right? And you contrast that to, let's say, writing 4 kilobytes in place, this is a very mean optimized part, and you're doing significantly more work on this part. Prior to SplitFS, all this stuff also used to go through. Okay? So we're basically saying here are some operations that are simple and you can do from user space. By simply moving them out, you get significant benefits. Yes. Yes.
What of benefit?
Yes.
Don't involve kernel and like how do you do zero copy?
Yes, yes, yes.
Is that something similar?
So here, the copying itself is not like the major thing. So there is one copy like from DRAM to persistent memory when we're doing all of these things. But within the file system itself, we do have to take care that we are not writing the data multiple times. So similarly, correct, correct. So here we have one user space copy and one copy. Yes. Yes, it's very similar. Yeah. I think exactly the same philosophy in a different sort of subdomain. Yes.
And can you say that the function benefit is coming because we are not tapping into the kernel multiple times?
Yes. So the kernel trap is part of it, but also what we do inside the kernel is also part of it. So for example, let's imagine that we introduce the kernel trap in this part, right? It would still be faster than that part. Because what we do inside the kernel has been significantly simplified. So both of those. Okay. All right. So we will see what we can get through with respect to that. All right. So now I'm going to talk about how do you build data structures for persistent memory. Okay. So I'm talking about things like hash tables, B trees, and so on. And we want our data structures to be concurrent. So we want multiple threads, multiple cores accessing them. We want to get good performance. We want it to be crash consistent. These are now durable data structures that we're talking about. So if we crash, we don't want a malformed tree or anything like that. It still has data has to be available. It has to be non-corrupt. We also want to be cache efficient, right? So all of these persistent memory is going to be accessed via user space, sorry, CPU caches. So we want to be efficient in how we bring the data into your caches. So concurrency is a hard problem. Crash consistency is a hard problem. Together, significant source of fun. So when we did this work, we actually took the current sort of best work, best state of the art work. Fast and Fair is a BT designed for persistent memory. CCA is a hash table designed for persistent memory. And we actually found significant bugs in both of these things, right? So corruption, data corruption bugs, availability bugs, and so on. Right? So the sort of main question we asked ourselves in this project is, we have had DRAM data structures for a really long time, like several decades. Is there a way where we can leverage all of that in building persistent memory data structures? Can we convert existing DRAM data structures to persistent memory data structures? So that's the question. And the chief insight that is covering that is that if you look at the world of concurrency and DRAM data structures, they provide isolation using certain mechanisms. Right? So you have two threads which are working on something at the same time. We provide isolation between them. It turns out that that isolation can be used to get crash recovery in persistent memory data structures. So this is very abstract. So I'll give you multiple examples to tell you what I mean. So if you have a concurrent data structure, isolation ensures that if you have concurrent writes going on, like multiple threads that are writing, during this time, if a read happens, the read always returns the correct value. So imagine that one thread is updating something big, you have a concurrent read, the read does not return a partial value, it returns a correct value, right? Either before or after state. Crash consistency ensures that despite an arbitrary number of crashes, so you wrote something or you're writing something and there's a crash, maybe you're recovering and there's a crash again or whatever, and then you're doing a read. So between the writing and the reading, regardless of the number of crashes, the read returns a correct value. So that is what a crash consistent file system provides. And it turns out, like these are like very similar concepts if you squint, right? And folks from Michigan were the first actually to establish this connection in a paper called Memory Persistency in ISCA, where they talked about how it turns out crash recovery and like isolation are like kind of related, right? So did that say? And what we are doing is we're going to like one step further. Right? So there they were like these concepts are similar. We are like we can reuse the implementation mechanisms itself in DRAM data structures to get crash recovery. So at a code level, these things are similar, and we can use that similarity to get crash recovery. That's the chief idea. So let me show you an example, right? So imagine that you have a lock-free B tree. showing you just the least node of it. There's 1, 2, and 5. Okay. So you have one person who's writing it, and imagine there's a way that you're going to do this, right? If you first copy over the key before, so you want to have a way, so you're copying over that and you're trying to write that. And then in the second step, you update it. So there's an intermediate step where there's the 2 2s, and then you have 1, 2, 3, 5. Now, if a reading thread was seeing this while the writing thread was going on, remember that it's a lock-free B tree. It may see something like 1, 2, 2, 5, a partial state. Right? Now, what does the thread return to the user as the contents of this node? It will return 1, 2, and 5. So even though it sees 1, 2, 2, 5, there's enough knowledge to ignore the duplicate, basically, right? So the reader can detect and tolerate duplicates. So that is the inbuilt mechanism here. Similarly, imagine that another writer sees something like 1, 2, 2, 5, right? So now we have a little bit of a more complex situation because in one case, the other thread may be actively writing, in which case you just have to wait. The other thread may have crashed for some reason, and then this other thread will actually complete this operation. So here we have to borrow a little bit from the theory community, who has also worked on a different version of this problem. So they call this a helper thread. So one thread was trying to do something, it crashed for whatever arbitrary reason. Another thread comes along, it sees this sort of like partial state. It then rolls back or finishes that operation. So it finishes the work of the previous thread. It's called a helper thread. Okay? So the writer fixes the inconsistency and removes the duplicates. Right? So now it's actually gone back to the old state. So it's removed the duplicate 2 that it previously saw. Okay? So if you have a writer which can detect and fix duplicates, it turns out this is what you need for cache consistency. A reader who can detect and ignore duplicates or inconsistencies, and a writer who can detect and fix inconsistencies. So if you have these mechanisms in build, it's actually simple to use them for cache consistency. So in the paper, we actually categorize DRAM data structures into different kinds. So there's one kind, for example, where the data structure is updated by an atomic pointer switch. Another type where the writers fix inconsistencies, and another type where writers don't fix anything. The details are not important, right? I'm just going to show you one example of this. So this is a very basic one, right? Like we have some data, and the way in this particular data structure is updated is you make a copy, you update the copy. So at this point, nobody else knows about it. So it's like private data, and then you switch a pointer. So from here to here. This then is garbage file. An atomic pointer switch. This pointer changing happens atomically. Okay. So imagine you have a DRAM data structure which is already doing this, right? So the update is done by a single atomic pointer switch. Now, if you took this data structure and then you put it on persistent memory, what do you have to do, right? It turns out that you don't have to do much because already what they're doing is called copy on write in the file systems world. It's already atomic, and regardless of when you crash, you only see one copy of the data. The important thing that you have to do is that in DRAM, you don't have flushing, right? So you don't really care about durability of data, but you now do in persistent memory. You have to add the appropriate durability semantics. You have to ensure that the pointer is appropriately fenced and flushed. Meaning, you have to flush this first before you flush the pointer. That's all you have to do. You can take the entire implementation. If you can figure out where these things happen, you just change some lines. Let's look at a slightly more complex example. So here we have a writer, which is doing this, and the writer, like we have an earlier writer which is trying to do this. Say another writer which is coming along and doing this, right? So readers detect and tolerate inconsistencies. Writers detect and fix inconsistencies. That is how the data structure already is. Now again, in order to convert this to a persistent data structure, all you have to do is to ensure that all the writes are properly flushed and fenced. Okay. So if you think about like what that will look like, we have multiple steps here, right? We have a thread doing step 1. Once it's done step 1, we want to flush it and we want to fence it. And the fencing will ensure that the later steps go to persistent memory after this step. So this becomes durable first, then this becomes durable and so on. In our project, when we converted this data structure to persistent memory, we took a very brute force approach. Once we identified what the steps were, everywhere we did flushing and fencing. You can imagine there are more optimized and cleverer ways to do this, but we didn't explore that. So it was just like the brute force thing. And so we have other types as well, but I'm going to skip this for now. But anyway, what happened when we did this, right? So the paper is called Recipe because it's a recipe for converting data structures from one type to another. Once again, done in collaboration with Georgia Tech, and we converted 5 different data structures: hash tables, B-trees, radix trees, and so on, all different kinds. And what we found was that in our worst case, we only had to modify 200 lines of code. Okay, in some cases, we had to modify 5 lines of code. This is a slightly misleading stat because, like, you are paid the big bucks to know which lines to change, not the number of lines to change. But still, like if you had a patch for the conversions that we did, you could see them on one screen, right? So an expert could verify them very quickly. And we got phenomenal performance, up to 5 times better performance in multi-threaded workloads than the handcrafted, designed from scratch indexes. And the reason we got such good performance was that we were building, standing on the shoulders of giants, basically. We took very good DRAM data structures, like for example, Mastery, if you've heard of it, very good performance and so on. So we took the best DRAM data structures and then we converted them. So we were able to preserve their good properties while adding persistency and cache consistency.
They modified the existing DRAM structure.
All of these things were like open source, the things that we modified. So
you took open source libraries,
yes,
trees.
Correct. Yes. So Recipe is also open source, and we have 5 different data structures that we have. And depending upon the particular workload that you have in mind, one of the data structures might be a very good fit for you. So if you want a persistent data structure, high performance, come talk to us. We're happy to help you. So one big theme I want to sort of call out is reusing existing code, right? So if you look at the 2 projects that I talked about, in both of them, we were reusing existing code bases, either file systems or data structures that were already there, right? So even though persistent memory is new, there have actually been decades of research into very similar things in DRAM, right? We have had file systems, block-based file systems for a really long time. We have had DRAM data structures for a really long time. The challenge is how do you actually do sort of surgical changes to these existing artifacts to satisfy our new research goal, right? And doing this, if you do this well, it actually helps adoption, because if you were to tell people I have built this new 50,000 line persistent memory file system, they'll be very skeptical to use it. But if you tell them it's mostly ext4, but it's some small changes so it's now faster, they'll be like, yeah, that seems more reasonable. I'll take a look at that. So it helps adoption a little bit. And if you want to do this carefully, right, it requires a lot of innovation, because in some sense, you have a lot of constraints now. You're stuck with this code base. You have to figure out how to reach this goal without having to rewrite the whole code base. And so it's very enjoyable. Our RTC was very enjoyable for us when we were doing this. All right, so we have 10 minutes, so I don't think it's going to be a lot of time. So I am actually going to go through sort of one more work very briefly, and then we'll sort of conclude. So in our group, we have looked at a lot of new applications like machine learning, blockchains, GDPR. And the central question we try to answer is, how should storage systems sort of evolve to meet these goals? So one project I'm going to talk about today is where we looked at storage for machine learning. Okay, so this was done by my student Jayashree in collaboration with Microsoft Research. When we began this project, right, the prevailing wisdom was that if you're training a machine learning model, what is important is just the GPUs. So the number of GPUs that you have, how fast the GPUs are, that is what matters. Doesn't matter what storage you have and so on. In some sense, this is still true today. So if you go to Amazon or Microsoft or whatever, and you try to rent a server for doing machine learning, your cost is directly proportional to the number of GPUs that you have. So if you want a machine with 2 GPUs, you want a machine with 4 GPUs, it's going to cost twice as much. It's all very much tied to the GPUs. But what in this project we showed is that it's actually not really the case. So imagine that you have this particular pipeline, where you have stored your data in an SSD, right? And you're going to see this entire data pipeline and what's going to happen. So initially what you will do is when you're doing training, you're going to read your data from the solid state drive, you're going to cache it in DRAM. Okay. Now, typically this data is compressed and encrypted when it's stored, right? Encrypted for security reasons, compressed to safe space. So you at least have to decompress it, even if you assume you're not going to decrypt. And then whenever you're training on this batch of data, you have to apply random transformations. So if you take a bunch of images, this is things like cropping the image, rotating the image, and so on. Because in every cycle when you're learning, you want to provide slightly randomized data, not the same data every time, right? And then you're going to feed it to your GPUs. Okay, and let's imagine that we have 8 V100 GPUs in this particular example. How fast can these steps go? So if you're reading from, like, let's say an enterprise grade SSD, you can read at about 500 megabytes per second. If you are reading it from your data cache, and let's say you have like a reasonable speed rate, overall effectively you get about 800 MB per second. Reading from both the DRAM cache and from the together 800. We're going to decompress that. The decompression rate is going to depend upon the CPUs. You're going to use your CPUs to decompress. You can decompress at 1300 MB. Then you're going to apply your random transformations. Again, this is a CPU specific activity. You're going to take your CPUs and take this image and crop it and rotate it and so on. Once all that is done, then you're going to feed it into your GPU. Okay. So you can do your random transformation at 700 MB. Unfortunately, in this particular example, your GPUs need about 2200 MB per second to not be idle. That is the rate at which they can process data. So if you look at it this way, right, you immediately realize a number of things. So one of them is that, for example, if you took this and you added more GPUs into this particular machine, you are wasting your money. You can't even saturate the GPUs that you have. Right? The particular bottleneck that you see here is applying the random transformation. So if you were to move to a machine which had more number of these CPUs, that would help. Right? In this particular case, your storage is not the particular bottleneck that you have. So even if you added persistent memory here instead of like SSD, it's not going to help. Flow right there and only bottleneck at the right. So if you look at our yes, sorry. Yes, so I mean, but like right now, the current bottleneck is our transformations. So if you were to increase your transformations to let's say 1400 MB per second, you would see a different bottleneck. Yes, at that point, the bottleneck would become the rate at which you ingest data. I mean, but like if you have a setup like this and you're doing like one action to try and relieve the bottleneck, it has to be whatever is the biggest bottleneck at that point. Okay? So so if you look at like our ML optimized servers from Amazon and Microsoft today, a lot of them you see similar situation as what I'm showing, where there's not enough balance in the resources that they're applying to the problem. So they typically have like very like beefy GPUs, like giant GPUs which can crunch a lot of things, but then they will give you like a very wimpy SSD, right? Or like all the data is accessed over the network from some region. And then the question is like, it doesn't matter how big your GPUs are. The data has to come through a very slow link and like every bottleneck on that. So yes.
So those transformations that you talked about.
Yes.
You have multiple parts of training, which is what generally
yes.
Is now. Is it possible that these transformations change every epoch or they're fixed for all?
Every epoch you have to do random transformations.
Different transformation
every time. Yes.
You
can do pre-compute some of them, but like if you're doing let's say 100 or 500 epochs, pre-computing all of them would be hard. You can definitely pre-compute like let's say 3 epochs or something and keep that in storage. But a lot of this also depends upon the other resources in the system. So in the example that I'm showing here, we are doing we are using every resource possible. So we're doing pre-fetching wherever we can. Every CPU that is there in the system, we are already using. Every link in the system, we are already fully saturated. Right? So there's no slack in the system. You have to add some other resources. Yeah. Um, the operation is the same. Like you can imagine operation like rotate, for example, right? The operation is the same, but every time you have to pick some new data and then apply that, and the resulting process data that you get, that is new for every data. The operations are the same, right? Yes. Yes, NLP it doesn't have this problem at all, right? So everything that I closed here is only true for data-intensive machine model. So, for example, if you have an NLP model and you can cache the entire thing in memory, right? The data of NLP is typically like very cacheable. Then you don't run into this problem. If you don't have to do significant transformations that require a lot of CPU power, you don't have to do that. So it's very dependent on the exact the model that you're training, the exact hardware that you're training on. Yes. Could you speak up a little bit, please? What makes them not GPU friendly? Couple of things. So one of them is that it's very general. So GPUs are very good at certain operations, but like if you take a wide variety of models, the transformations required also change. Transformations required for some vision tasks are different from, for example, bounding box or rotate or crop. And the GPUs are not particularly good at doing all of these operations. So NVIDIA has something called DALI, where you can offload some of your CPU operations to GPU operations. And the experiments that I'm showing you, we are using that already. We're already using DALI to offload whatever we can from the CPU to GPU. Even with that, the DALI does not support all of your CPU operations. Even with that, you still have one. So you can imagine, like let's imagine that like we are a startup and we have like one workload that we want to optimize, right? So the clear answer is that we want to produce some sort of like chip that will do the exact operations that we want to do. And there are startups that are doing something like this, right? So if we for a general training, it's harder to do that because there's just like so many different operations. But if you just like want to optimize for one thing, you can build an FPGA or like a chip for exact those operations, then it will become much faster.
DNA training is all for the TensorFlow.
Yes.
But that is all just code and there are no good alternatives or like it's used often like this on so my question is how do we address that? Is there more codes to help there?
More codes do help, and sort of like hardware, specialized hardware to do these transformations also. So those are the two things. And for other bottlenecks, like for example, if your data throughput is not high, adding like more SSDs so that you have an array that gives you higher throughput, that would help. Sometimes what will happen is that you have enough bandwidth here, but not enough data cache. So adding more DRAM will help. It all depends upon the situations that we have. So we have built a tool for this, right? What the tool will do is it will take the exact model that you have, run it through whatever hardware setup you give us, and it will basically tell you everything I've told. Like what the bottlenecks are, what will actually help. And this is meant for basically non-Facebook, non-Google data scientists who are renting machines on Amazon or like that. So who don't have domain expertise for this, right? Yes. Yes. Yeah. Yes. No. So that's a good question, right? So what I talked about is where we are viewing the ML model as sort of like a black box. We are not changing anything inside it. We are not changing how it processes the data, anything, right? There has been lots of very interesting work on like the ML side of this whole equation, right? Can we, for example, work with like lower amounts of data, right? Instead of like processing terabytes, can you identify like a core? And you do the transformations in an easier way, like other semantically equivalent transformations that are computationally more efficient. So I'm not talking about any of this stuff, right? There's a whole world in sort of like ML where they're working on like optimizing these things, right? But I think the sort of unique thing here is that this is a big high-level systems view of it, right? So people are optimizing like step by step all of these things, but overall what's happening is what you see. So we are in fact out of time. So I'm gonna like quickly sort of like wrap up. Um, so oh, okay, all right, all right. So okay, so what is the high level thing that I want to sort of say, right? Is that we call them data stores, right? So computer architects already have data stores, sort of like CPU pipeline. It's a very similar concept. So you want to keep your GPU sort of right? So we have different stalls and we have different names for these things. So we call this a fetch stall. You're trying to fetch data, that is becoming a bottleneck. And you also have like what we call prep stalls, right? Where you're trying to prepare the data for processing, and that's become the bottleneck. So depending upon what stalls you have, we have different ways to handle it. I don't want to skip over all the rest of the stuff. I'm going to skip over this stuff also. Lot of stuff I'm skipping. But let me talk about this like for 5 minutes, right? So what are the challenges that I see in the future when you're working in storage research? So one thing that we have seen is that the line between memory and storage is blurred, right? So if you look at like things 10 years ago, the set of things you would do for storage systems, the set of things you would do for like memory management is very separate. Now it's actually become very meshed. And we have the work called WineFS in SOSP, where we show that huge pages have now become very important for persistent memory. Most applications, when they try to access persistent memory, they map the data. And so whether you get huge pages or not becomes a very big thing. And huge pages have traditionally been sort of like the land of memory management. But we show that file systems actually have a big role to play in whether you would eventually get huge pages or not. For example, if your data is fragmented and all over the place, there's no way you're getting huge pages on the fragmented data. And this is important because many persistent memory file systems, they use a log structured design, which basically means that every time you update, you write in a new location. So your data is spread all over the place. No hope of getting huge pages, but vitally important for persistent memory. So we talk a little bit about stuff like that. How do we build storage that enables compliance to regulations, like GDPR, for example? So GDPR has limitations on when you can store the data, how long you can store it, when you can process it, and so on. So we have a communications of ACM article about this last year called GDPR anti-patterns. So recommend you check it out. There are other challenges closer to verification, right? How do we verify existing storage systems that are written in C, right? We have a number of systems where it's written in some high-level language and it spits out a verified artifact. But all of the file systems in Linux are in C. What do we do for those if someone will work? Now, how do you build disaggregated storage systems, right? A trend that we're currently seeing is that instead of having each server have CPU, memory, and storage, people are pooling together the resources. So in a cluster, you would have one pool of memory, one pool of persistent memory, or storage, and so on, right? How do you build systems for that? It's something really nice. So in conclusion, right, it is a very exciting time to be a storage researcher. There are new applications, there are new storage devices, it makes it very exciting. My sort of personal plea is to try and use existing software artifacts to solve these research challenges. And when you're trying to do these things, right, oftentimes you need to go and talk to theory groups, right? So Recipe, PebblesDB, all of these things are powered by theoretical insights, actually. So, and when you find the right theory collaborator, it's amazing, right? You go to them and you say, I have this very hard problem. Then they're like, there's actually a paper in 1930 which solves this problem. And it's just to take it. So it's a lot of fun, but you need the right sort of mindset to collaborate with theory folks. It's a lot of fun and I highly recommend it. With that, I'd be happy to take any more questions.
If I take one question.
Yes.
So I understand the desire to stay in the existing source code, but over time, there is layers and layers and layers of unnecessary stuff built into it, right?
Yes.
So I wonder if you actually step back from your first work where you showed the kernel.
Yes.
And you say, I'm going to build something completely from scratch for a persistent memory storage. How much better did you get? Did you get to 700 at that point? I
don't think we'd ever get to 700, but we'd be fairly close. I think for the data part, it's actually harder to do better because we're already minimizing our extra latency quite a bit. But for metadata part, you can do significantly better because like right now in that project, we were basically saying whatever ext4 is doing, we're just going to do that. That is of course very inefficient and old and stuff. And I haven't talked about this, but we have in fact ourselves built other file systems, right? Where we have done the kernel approach, where we have like re-architected inside the kernel. So there's definitely good work to be done there. Yes. Sorry, could you speak up a little bit? Yes. No. Yes. Then the ratio will definitely go down. Now, some of it is that there are like fixed overheads and like per KB overhead, right? So some of it is like fixed overhead, like wrapping into the kernel. So that's a fixed overhead that you see, right? But some of it is that even if you, for example, did a 4 JB thing, the core parts are still pretty complicated. What you do for each page will still be sort of like more higher overhead than what you do on the data file. So the ratio will be better definitely, right? Like here it's like 10x overhead. There it will be like 2x overhead. I'm not sure. I'm making this number up. It will be like a lower overhead, but the overhead will not go away, right? And for many applications, it is impossible to do sort of designing. Correct. Yeah, that's a good question. Just to repeat the question, right? So in the sort of like graph or the figure that we saw that data was being read from storage into memory. The question is, can we simplify storage given that ML data is like static, immutable, and it's read multiple times? Can we use that to design better storage? Right? And the answer is yes. And like lots of people have looked at this, and we have looked at this ourselves. The unfortunate thing is that like the gains are not very high. Like the things that you can do in software to reduce it is actually quite low, right? Because like ML is actually the reverse of the thing that we saw where we were like appending like 1 4 kilobyte unit, right? ML workloads typically are like lots and lots of files over many inputs. So it's more a throughput game than a latency game, and there you get very much limited by the bandwidth of the device. So all the software things that you go like in the noise compared to the bandwidth of the device. And so like there's limited things you can do in software to get better performance.
Just technique. But you should do the small things so that the overhead dominates. But how about larger
Yeah. I mean, like I think like it's basically like what was previously asked. I think so. As you increase the data unit size, with the overheads like you mentioned, right? And some overheads would remain, like like basically the cost of wrapping the kernel, for example, would be there. But your other overheads would become smaller. So I would say like the overheads do not entirely go away by using a larger unit size, but definitely the ratios that we saw would go down. Like right now it looks like 700 nanoseconds and that's 9,000 nanoseconds, right? If you did like let's say like 4 gigs of data, right? Then those two numbers would be closer together. Yes. Let me see if I understand correctly. So you're asking about heterogeneous storage hardware, or?
Like that.
Yes.
Just like person memory be like a cache within SSD.
Yes. So typically, like in all of the problems that we saw, we are already using both DRAM and some storage unit, right? So we could expand the mix. We could add like personal processing memory. But again, like it becomes like very much a point of like like what is the workload doing, right? So persistent memory is really good for random latency sensitive operations. Like for example, like a random walk on a graph. So you can load the entire graph into persistent memory, and then like any node that you're touching, you can actually read quite quickly. And this is a use case where you can't really cache well, like the pattern is random, the data set is very large, so persistent memory helps a lot. For other workloads where like the pattern is sort of like pretty regular, then even if you had persistent memory, you could actually get very similar performance with a small amount of DRAM. So it's very workload specific. Yes. The question is, if you took SplitFS and you ran it on an SSD instead of like persistent memory, would you still have gains? You would still have gains. Not as much as we see here, but you would still have gains. Now, the thing to remember is that the source of the amazing performance improvements is that on the sort of like an expensive path, you're doing a lot of CPU operations. And because persistent memory is so low latency, every CPU operation you do in relative measure, it becomes very expensive. But if your storage itself is very heavy, like 20 microseconds, you can do a lot of CPU operations in that bandwidth, right? So the slower your hardware is, the less useful something like SplitFS is. Yes.
Is there a study which tells about like how frequent are data operations as compared to normal data operations?
Yeah. There's been like lots of like papers and like SIGmetrics. That's where you should go look for that. And what they basically show is that in most workloads, data dominates. Like data reads and writes dominates the whole thing. And in fact, reads dominate everything else. Like most workloads are actually like read dominated. There are exceptions like the Git workload that I talked about, where like there is a lot of like metadata involved. But in general, if you are thinking about a database or key value store or some other data processing application, it's fair bet that most of them are reads.
Thanks a lot.
Thank you.
And,
Thank you so much.
thanks a lot for the talk.
Thank you, folks.